High-tech map shows you the missile trajectories. What does it mean is that while the world watches the skies over the Middle East, we are looking at the silicon. The conflict between Iran, Israel, America is not just about a battle of explosives as you see in the BBC or CNN. It is a battle of milliseconds. So today, we decode the actual code that powers the Iron Dome. So you see that the dense and the depthwise blocks. A standard convolution dense creates a massive computational burden that requires a data center to process. But you cannot fit a server rack into a 155 millimeter interceptor shell. To fit a brain into a missile, you have to shatter the math, shifting from dense to depthwise to make the AI lightweight enough to fly. Because you know that in case the missile consists of more battery, it means larger the size and difficult it is to control. So as you see the magic parameters, the standard confusion on the left hand side and the efficient switch depthwise on the other. What does it mean is that the secret weapon in standard convolutions you get channel crosstalk and network lag by 90%. And of that it is just math's burden. By flipping the efficiency switch to depthwise, you drop that math load to just 10%. We are not losing intelligence, we are just cutting the lag that kills. And what is that lag? The lag is the math load. So what we have done here is that we have coded the entire Iron Dome, and what we have known about is that don't take my word for it. Look at the proof. In our collab test, the mobile model is 9 times smaller and 12 times faster. What does it mean? That in case of an interceptor, those saved milliseconds are used to recalculate wind resistance and counter maneuvers. Speed is not just a metric, it is the difference between an intercept and an impact. I show you the code that I have done here. It is a very small part of what is being done behind the Iron Dome. And that is why this YouTube channel powered by Muhammad Qasim correctly says that the machine learning interception is what makes the Iron Dome worthy. The Python code defining the cloud versus mobile models. Let us look at the implementation. On the top, you see the cloud paradigm, a standard 2D convolution layer, and below it, you see the mobile version. Notice the groups is equal to 3. So what does it mean is that it is in the first layer and the one by one point-wise layer that follows. This is how you engineer for the edge. And by the way, you must be knowing what is the difference between cloud ML infrastructure and edge ML infrastructure. Cloud machine learning infrastructure basically deals entirely about the data centers. So you may face latency issues, connectivity issues. It is the deployment of machine learning models, as I earlier said, on basically on the data center infrastructure, offering massive computational capacity, scalability for training, as well as serving complex models at the cost of network latency and connectivity dependence. I say that in natural language processing computational demands, model language models like GPT-3 required 3640 petaflop days of compute for training, that is equivalent to running 1000 NVIDIA V100 GPUs continuously for 355 days, almost a year. So you see that this computational scale drove the need for massive cloud infrastructure. And by the way, the edge computing is what you say is basically on the localized infrastructure. and it is at the network edge, meaning that it enables low latency processing and data privacy through local computation on stationary devices like you must have heard about gateways and industrial controllers. So what does it mean is that if we see the output, what it shows? It shows the entire collab output that I just simulated, and it's the, you can say, 1/5 of the part that I am showing due to the constraints that I simulated the real world conditions by running 100 iterations of the model. And we wrap the measurement in torch dot no dash grad. And what does it mean is that we are importing the torch library and the gradient descent, because in a live missile we are not training, we are inferencing. So we are basically inferencing, and we need to know exactly how long a forward pass takes before the target moves another meter. So when I ran the code, I figured out that the terminal output shows 6.27 times smaller memory. It means that the results are final and accurate. By shattering the math, I achieved a 6.27 times reduction in memory and nearly doubled our speed. This is the blueprint for inference at the edge, taking high level theory and making it survive on limited hardware. So you see that the X-ray of the circuit board. So this is the chip that is involved in the IronDome. X-ray shows that you cannot put an NVIDIA H100 in a seeker head. Instead, we would use neural processing units. So these wires are hardwired to run our groups that is equal to 3. So groups is equal to 3 is a logic at the speed of light, and that bypasses the general purpose CPU entirely. So where the code lives entirely means that the NPU, the neural processing unit, commands the entire infrastructure. As you see closely, the groups is equal to 3 logic is hardwired. There is a seeker antenna array, CPU, GPUs, and the power management IC. It shows correctly that by looking closer at the neural processing unit NPU, that is at the brain, it has specialized vector compute tiles. This is not just software anymore, it is an FPGA bit stream optimized for survival. The code and the silicon become one single lethal defensive tool. As we move further on, we now get to know about the accuracy and the survival. What is the trade-off between them that is quite hindering the truth? So the hard truth of deployment engineering is that most people chase 99% accuracy, but in the field, it is better to be 91% right now than 99% right too late. A slow model, no matter how accurate, is just expensive scrap metal. We chase survival, not just scores. So the basic point to ponder is that you see a drone here and it is to be struck. So the thermal drone view with bounding boxes, this is the final result. Every flicker of those bounding boxes is a forward pass of the code we just analyzed. It happens 100 times a second. The AI identifies the heat signature, locks the coordinates, and triggers the intercepts, all locally with zero cloud dependency. So it shows correctly that even if there is a swarms of connected drones, the future is even smaller, tiny machine learning. We are talking about devices that run on kilobytes. Imagine a swarm of hundreds of drones, as clearly seen, all using distributed intelligence to talk to each other and overwhelm the defenses. So you see clearly that mobile machine learning is a personal and offline intelligence. While edge machine learning addressed the latency and privacy limitations of cloud deployment, it introduced new constraints. The need for dedicated edge infrastructure, ongoing network connectivity, and substantial upfront hardware investments. The proliferation of billions of personal computing devices created an opportunity to extend machine learning capabilities even further by bringing intelligence directly to users' hands. Mobile machine learning represents the next step in the distribution of intelligence because it prioritizes user proximity and offline capability. It also integrates directly into portable devices like smartphones and tablets. But what is to be seen is that mobile devices exemplify intermediate constraints. What about the 8 GB RAM, the 128 GB 1 terabyte storage, 1 to 10 tops AI compute through neural processing units? Because neural processing units consume about 3 to 5 watt power, and the system on chip architectures. Chip is hard to design. And what about the VLSI engineers that would be pouring all their material into the chip and at the end they would find a glitch? So that's a huge loss. And the memory bandwidth of 25 to 50 GB limits models to 10 to 100 MB parameters and requires aggressive optimization. Battery constraints are 18 to 22 watt per hour capacity, making energy optimization critical. 1 watt continuous machine learning processing reduces device lifetime from 24 to 18 hours. Specialized infrastructures and frameworks like Core ML and TensorFlow Lite provides hardware optimized inference enabling less than 50 millisecond UI response times. Although I agree that mobile machine learning excels at delivering responsive, privacy preserving user experiences, real time processing achieves less than 10 millisecond latency, enabling imperceptible response. Face detection operates at 60 fps with under 5 millisecond latency. So while the voice wake word detection responds within 2 to 3 milliseconds, Face ID processes biometric data entirely within a hardware isolated secure enclave. As I earlier stated about the coordinates, so the Google Maps analyzes millions of road segments locally for navigation, translation, and sports 40 plus language pairs using 35 to 45 megabyte models that achieve 90% of cloud accuracy. And what about the entire prediction that the app will be using with 70 to 80% accuracy? And about the camera systems, they continuously adapt to user preferences through feedback. So what does user mean is measle. So the measles benefits require accepting significant resource constraints. As you see that the mobile ML has achieved transformative success across diverse applications, but the computational photography represents perhaps the most visible success. So, the entire conclusion is that we need to think about the tiny ML, that is ubiquitous sensing at scale. The progression from cloud to edge to mobile machine learning for missile systems demonstrates the increasing distribution of intelligence across computing platforms. But each step still requires significant resources. Even those specific softwares operating ML mobile with their sophisticated processors and gigabytes of memory, represents a relatively privileged position in the global missile computing landscape and demands watts of power and hundreds of dollars in hardware investment. Tiny ML brings intelligence to the smallest devices, from the microcontrollers to embedded sensors in missiles. They enable real time computation in severely resource constrained environments. And power applications such as predictive maintenance, environmental monitoring, and what I see about the simple gesture recognition, the missiles are optimized for energy efficiency and the batteries can run for months. But how do you think that tiny ML, that is all about the deployment of machine learning models on our microcontrollers and ultra constrained devices that enables autonomous decision making with milliwatt scale power consumption in the missiles industry for applications requiring years of battery life? The thing here is that tiny machine learning, extreme resource constraints enable unique advantages, and perhaps there are trade offs. So the microsecond level latency eliminates all transmission overhead, achieving 10 to 100 microsecond response times. But not here. The vibration monitoring processes of missile industry is about 10 kilohertz, sampling at under 50 microsecond latency. And while the Israel-Iran missiles have been quite discussed, but what about the environmental and health monitoring? It is catastrophic. The model compression in the missiles are the techniques that you see are used to reduce the model size and computational requirements. But these methods can achieve 10 to 100 times size reduction while maintaining 90 to 99% of original accuracy. The environmental health, you see that the sensors that cost 50 to $100 compared to traditional wide sensors that stays at 500 to $2,000 per point reduces the deployment cost from 5 to $20 million for 10,000 monitoring points. So the local anomaly detection provides 7 to 14-day advance warning of equipment failures, and that equipment enables the missiles industrial manufacturers to achieve 25 to 45% reductions in unplanned downtime. So what have been taught here is that the train serve split is one of the most common hybrid patterns in the missile machine learning, where model training of the missiles occurs in the cloud but inference happens on edge, mobile, and even tiny devices. So this pattern takes advantage of the cloud's vast computational resources for training phase while benefiting from low latency and privacy advantages of on device inference. So you see that the missiles that are trained have been used quite often in the war against Iran. So there are the concepts about the federated learning architecture that coordinates learning across millions of devices without centralizing data. As I often say that Google's federated learning processes 6 billion mobile keyboards training improved models while keeping all typed text local. Each round involves 100 to 10,000 devices contributing model updates. So you see it quite prominently that production systems demonstrate integration patterns across diverse applications where no single paradigm could deliver the required functionality. Industrial defect detection exemplifies model deployment patterns. Cloud infrastructure trains vision model on datasets from multiple facilities and then distributes optimized versions to edge servers managing factory operations, tablets for quality inspectors, and embedded cameras on missiles. This demonstrates how a single ML solution flows from centralized training to inference points at multiple computational scales. And they are the trackers that exemplify gateway patterns in the missiles between the tiny ML and mobile devices. So there exist a shared principles across deployment paradigms. Despite the diversity, all machine learning deployment paradigms share core principles in the missiles that enable systematic understanding and effective hybrid contributions and combinations. So as I see that the cloud ML data centers training at scale, the edge machine learning local processing inference focus, and the data pipeline collection, the processing of data, the data training, then the data deployment, and then the model monitoring, all leads and all depends further on the optimization and efficiency of the model. As I said, that mobile machine learning requires resource management, compute efficiency, energy network. Tiny machine learning consists of embedded systems that are resource constrained. So what I need to hear is that it is quite often that the decision framework for deployment selection is quite realistically about the selecting appropriate deployment paradigm for systematic evaluation of application constraints rather than organizational biases or the technological that encapsulates in the missiles. So thank you.